Hi everybody. Well, last time we discussed the assembly directives, and we mentioned that we have the control directives and data directives, and then we discussed some of them. And for control directives, we focus on ORG and END. That's what we have become very familiar. For the data directives, and we discussed the IMB and the FCB and FTB. Well, today let's finish the rest of the data directives, which is the FCC and the EQU, and then we will do some exercise. So I think we stopped here for the FDB. Yes. Okay. Now let's talk about the FCC. Okay, FCC is short for a form constant character. Okay, so in comparison between FCC and the FCB, that one FCB is for data byte. This one for constant byte. This is mainly for number. Okay, mainly for number. So we reserve a block memory, then, and for each location we save we initialize this value by 1 byte of data. So it's mainly by numerical value like this. Yeah. In comparison, for the FCC, is mainly for the characters, like alphabetic characters. Yes. So for each byte, okay. So for each byte, and we save a character. Of course, it's saved in the form of hexadecimal, or I should say, it's saved in the form of binary bits. So we reserve and also we initialize this value. Okay. Now, so how do we present the characters? Okay, as I show you here, we go. You see, we put in double quotes. So the characters we can initialize the reserved memory. They are here shown us within double quotes. Well, some assemblers they also allow us to use a single quotes. Okay, instead of double quotes. In our book, okay, we sometimes use double quotes, sometimes use single quotes. So either way is fine. Here I show you an example. FCC here I changed to use the lowercase instead of the uppercase, which have been used all the time. So we can use whatever the uppercase or lowercase. So FCC, the double quotes, then the characters are DEF. That means what? We're going to reserve a block memory. Okay, yes. Then for each location of memory, we initialize this value by these characters. Okay, in other words, what? We fill out these reserved memory blocks by these characters DEF. Here we also labeled alpha. Okay, that's the same way as I showed you before. Like here ABC, or here the TMP, same idea. Okay, that's where we can refer to this block of memory and in the rest of program when we program. So now, after we initialized the values of memory by these characters, okay, so this can generate, okay, those three values, 64, 65, 66 in hexadecimal in memory. In other words, although we initialize this block of memories using alphabetic characters, but when they are saved in memory, they use binary. Okay, they use binary, okay, 0, 1, and their hexadecimal equivalents are 64, 65, or 66. Okay, now what are these? These are the numerical values. They correspond to the ASCII, the characters of the D, E, F. So those corresponds to D. This is for E. This is for F. 6 for 6. Okay. Then what? Then as I said, the assembler we use label alpha. Alpha here we use label alpha here. We use alpha here we go to refer to the address of the first letter, which is 64. Okay. So always make sure. Okay. Although we label our reservation, but when we label, although we reserve the block memory and we label it, but the label actually refers to the first address, okay, which is here 64. Now, so you may ask me where the 64, 65, 66 they came from. So in next slide, I'll show you the defined ASCII, the printable character conversion table. So this table is pretty much complete. It shows us for each alphabet letter or characters or space or different symbols we use. Okay, we use what? We use English, or we use or they are on the keyboard. Okay, we can see what's the corresponding ASCII, hexadecimal, and binary, and decimal. Okay, we see right here a moment ago, what we type in is DEF is make sure they're lowercase. Make sure, and then in ASCII, okay, and the lowercase and uppercase are different. So let's check where's the D. D right here. D is this one. D is right here, this one. This one. This is D. The lowercase d right here, so we see is equivalent the hexadecimal numerical value in ASCII is 64. Make sure this is not 64. It's 64. Not decimal. It's hexadecimal. Its decimal is equal to 100, not 100, because this is decimal. So it's 100. And is the 7 bits. The 7 bits binary notation is 1100100. This is exactly what equals to 64. It's 1100100. Okay. And then for E right here, so for E is right here, next one below the D. E right here is hexadecimal equivalence is 64. It's 65. So in decimal is 101. This is decimal, so 100, 101. And binary notation is 1100101. So then if we convert to, so that is then when we convert this binary into 65, then into hexadecimal is equal to 65. 65. We assume like here we go, and then we have nothing ahead of what the first bits, because ASCII bits right here, and they use only 7 bits notation. It's 1100101. That's equal 65. Same idea for F. F come here go is 66. So it's 1100110. Okay. Now, so that's why we see right here 65, 64, 65, 66. The different. Now, however, if you have here if you have here is the uppercase, the D, E, F, then it's different because for ASCII they're different. Lowercase and uppercase are different. So if they're uppercase, then let's check the table right here. It's D, E, F. That would be this one, this one, this one, this one. Then the value is 44, 45, and 46. It's quite different. And the corresponding decimal is 68, 69, and 70. Those are different. Now, so So the value, okay, we save in memory actually is what? Is the binary notation or hexadecimal notation, or the binary equivalence or hexadecimal equivalence of what? Of this character, okay, according to ASCII table. Now, so you may ask me why here we only have 7 bits is here for the DEF here. D is 110. All these are only 7 bits. So let me show you here. All those they are only 7 bits. They're only 7 bits. See, 110 is 110,000, and come here 6 come here. D is 110,010. Because for ASCII characters they only define 7 bits. So the leftmost bit or the highest order bit, which is the bits right here, should be added here. Add here is bit 7. This is bit 0. First bit 0, then bits 1, then 2, 3, 4, 5, 6. Bit 7 is missing. Bit 7 is what? Is the parity bits. We should add there. We should add it in front of this. If we should add it in front of the total 7 bits. That's mainly for parity check. Okay, so that depends on what type of parity we use. We used odd parity or even parity. Then what? We need to compute this leftmost bits. We add to there. Then we want what? We send out. Okay, so that depends on you use even parity or use odd. Okay, so if you use even parity, then you count the number ones you have. For what? For the 7 bits we already have. Okay, if they're already even, then we put the leftmost bits to be 0. If they're odd, then we put the leftmost bits to 1. Now, if you use odd parity in transmission, okay, if you use odd parity, then you got to make sure the total number of bits of 1, what, in your 8 bits got to be odd. So if you already have odd number ones in the 7 bits, then you put leftmost bits to be 0. Okay, if you have even number of ones in your 7 characters, then you put the leftmost bits to be 1. So you can have odd number ones. Then you send out. So when receiver receives each character, receiver will check to see if this character has error or not, based on by counting the number of ones that you have. It depends. You define it to have even parity or the odd parity. Yeah, like this way. So if you get a book, I think they give us some examples, and we can check it, especially in the appendix. And so let me see which appendix. Yeah, but I think it's pretty much clear. It's given somewhere in a book, and they also give us some exercises. So let me find out which page do we have them. So if you simply go to index ASCII, if you check our ASCII, it's page 471 61. And 471. Let's see 471. Yeah, 471. Yeah, so if you go to page 472, if you go to page 472, and if you go to page 471, at the bottom right here, they discuss the parity bit. Okay, they discuss the parity bit about ASCII. So I want you guys to take a look at them. So I think it's straightforward. But if you have any question, just come see me. Okay. So parity bits, which is bit 7 here, is missing. So that's why we only have 7 bits left. So the parity bits, it's bit 7. Okay, it's the leftmost bit. All the rest bits from bits 0 to bits 6, they are defined here. They're defined here in the table here. We see those. The parity bits is missing. Parity bits will be added. Okay, when we send out. Okay, because the parity bits is 1 or 0. That depends on we the system, the computer system, use odd parity or use even parity. Then what? Okay, so both the receiver and sender, they agreed what type of parity to use. So they will. This is what we call the what you put the parity bits, or the receiver will remove the parity bits like this. If you go to page 473 of the book, it gives you some exercises. They're very interesting exercises. I want you to read by yourself. So they are mainly covered in the communication systems in the book in chapter 10. But that's good exercises. So I just want to let you know, here for ASCII, the conversion table, only 7 bits defined. So this is FCC. Now, so you may ask me, when do we need it to use FCC, or what's the application, the scenario, or the program scenario that we should use FCC? Here, let me give you a very simple example. Assume now we're writing a program. This program is to give out the grades for a student. Okay, for student. Then, okay, the very important item we need is what? We have to include a student's name in the program. Then what? Then we can give the grades to each student. So we have to include our name. So if so, of course, what? I assume everybody's name is made using alphabetic characters. Okay, yeah. So that's where we use FCC. Assume now we need to initialize Mike. Okay, so because we need to save the student's name, Mike, in memory. So we use FCC. So the simplest way is this way. It is this way. We run FCC, form constant character. Then we put the name of students and the double quotes. Then we also label it, name. Then in the rest of the program, we can refer to the name and whenever we like. Whenever if we refer to the name, then it will come to this memory location where the Mike stored. This is best ways. So here we change the uppercase, but right here we use lowercase. It doesn't matter. So if you do so, then I said that if you can see inside the memory, okay. So after you do assembly, of course, because we only convert to they only convert the binary or hexadecimal in memory after you do assembly. So after the assembler do assembly process for this statement, then if we can see inside the memory, then what happened? Then in the corresponding location where we form the constant characters, or we reserve the memory for this FCC, then we can see the value corresponds to them is 4D, 49, and 4B, and 45. We have 4 characters. Okay, that's what each of this AMI, M, and I, and K, and E, they corresponds to. Okay, and also here we label them to be name. So I think that's very easy. We can check it. So AMIKE, they are 4D, 49, 4B, and 45. So if you go to right here, the table, we can see this. They're all in uppercase. 4D, here we go. 4D AM here. AM corresponds to 4D. And I here corresponds to 49. Not 49, 49. K corresponds to 4B. And E, it corresponds to right here is 45. So we have 4D, we have 49, 4B, and 45. Okay, that's where we come from right here. So most of the computer systems that use ASCII systems. Okay. So the name here refers to the address of the first letter, whose value is 4D. So that's pretty much for the FCC. The next one is EQU. Okay, the EQU, and we haven't used any. We haven't used EQU in any program yet. EQU its job, okay, is from equate. Okay, from equal is to equate a symbol with a numerical value, like we assign a numerical value to a symbol, or we assign numerical value to flag something, to flag symbol. We can use it. Then whenever if we hope to use this value, we simply we call this symbol. That's it. So we don't have to remember what's the exact value of the symbol, because if you name it a user symbol, it's very easy to remember. Like this. Or we simply said we assign a value to label. Yes. Here we either call the label, we call it either label or we call it symbol or label, same thing. Okay, so the symbol right here actually serves as label of the EQ directive. Okay, why? Because as I mentioned, okay, well, sometimes in your program, if your program is very long, you hope to define some constant, and this constant never change. But if you have a large number of so many constant, it may not easy for you to remember. Okay, so probably however, if you assign them to some symbols, if they are easy to remember, then whenever if you hope to use them, you simply call the symbol. Then it should work very well. So define some constant that use EQ can make our program to be more readable. Okay. Now when we equate using EQ to a symbol, then in general we equate a symbol to address, location, or to a numerical constant value. So the value we try to assign to this label is either address that we hope to remember, or address location, or a constant numerical value. Now however, because EQ is not an instruction, as we repeated for many times, is the directive. So even though you assign a value, numerical value to this label or to a symbol, okay, but however, this value is not appeared in memory, because you assign this value using the directive. The directives never have machine code in memory, so the values you assign to the symbols do not appear in memory. They do not appear in memory. Then, so in your program, whenever this symbol or this label appeared, assembler will convert these symbols into actual numerical value you assigned before storing a program into memory. Okay, so all these symbols are replaced by numerical value. Okay. So let me show you an example. Here we have two examples. Okay, the first one here. First one here, raw EQU E000. So if you look right here, I mentioned this from here. This is what the directive of ROM. Okay, like RAM. Here we go. It's on the label. EQU E000. Okay, so here it means what? We equate RAM. This is like a label. or sometimes we call the symbol. So in other words, we try to make these two values equal. In other words, we try to assign E000 to ROM. ROM here is label. Okay, but in general, if you use EQU, because it's already defined, the value right here after the numerical value after EQU is already a numerical value, so there's no need to put pound sign. In other words, right here we don't need to put pound sign, because E00 is already a numerical value. So here it means what? We equate this symbol ROM by E000. So whenever in the rest of program, if you use ROM, okay, then what? Then when we do assembly, its value EROM is replaced by E00. Okay. Here actually is what? Actually we sign ROM like a read-only memory. Here what we're doing is what? We try to reserve we try to make the read-only memory start at E00, like this way. Let's take a look at the second example. This one. Loop, count, EQ. Here is 40. While this is here we go. This is using hexadecimal, because we use dollar sign here. But here we have nothing ahead of 40. That means 40 is decimal. 40 here is a decimal. It's 40. That means what? We sign loop count as 40. That means what? We make this to equal 40. That means what? Well, we define a loop to repeat for 40 times, or to run for 40 times. Okay, like this, because its control is with counter loops. Here we can either using decimal or even binary or hexadecimal, as soon as the notations are clear. So here I give some more explanations. The first one here refers to memory location E00 as the start of read-only memory. Okay, but of course you don't have to define to be ROM. You can define something else. Okay, the name here we go is only a label. Okay, then what? Then in the rest of the program, whenever the ROM appeared, whenever ROM appeared in your program, it will be replaced by E00. Then in this case, okay, the programmer when you run the program does not have to remember what's the value of ROM, because you already signed to ROM. You simply call ROM. Okay, you don't have to remember E00. But if you only have one label, like here EQU, then it's easier for you to remember. It's E00. But if you have 50 or 100 so many symbols, then what? It will not be easier for you to remember the corresponding value. Here we go. But because you already assigned them to interesting name, interesting labels or symbols, so but you may still remember, okay, labels. Okay, so you can simply call the labels. Same idea here for loop count. Okay, whenever the loop count appeared in your program, okay, it will be replaced by a value of 40. So that's pretty much what we prepared for the lecture of assembly directives. So at the beginning we discussed about some rough ideas of assembly directives, and then we finish the rest of several assembly directives. The next time we get to discuss the address mode, and then also make sure we have homework. This is homework 3, and we have 2 problems on the fundamental, 1 problem on the advanced, and 1 problem for challenging. And I will announce when this problem needs to be turned in. So that's pretty much the second lecture we prepared for the assembly directives.